Hello again, everybody, and welcome back. We're beginning chapter 5 on Newton's laws of motion and, in particular, forces. And no doubt you probably heard of some of Newton's laws before, and you certainly know about some forces. We're going to look at these in more detail, and some terminology that you've probably heard before, terminology like inertia and net force and that kind of thing. We're going to look in more detail in this chapter. So let's just go ahead and get started. So what is a force? Well, back in the late 1970s, as George Lucas was creating his epic space series, Star Wars, he came up with the idea of this ability to influence objects either nearby or at some distance, and he called it the force. That's really what a force is. It's the ability to influence something. For our purposes, mostly it's going to be by changing the velocity, making it move, or making it stop moving, or changing its rate of motion. Sometimes you can say, you can definitely say that forces can cause something to change shape. We're not going to look at that as much. Most of it is going to be with regards to changing velocity. We measure forces in something called newtons. It should probably be obvious where that came from. A newton in the international system, or the metric system, is the same kind of measurement that a pound would be in our English system. The only difference is that a newton is roughly what you would call about a quarter of a pound, a little less than a quarter of a pound. So pounds in the English system, newtons would be in the metric system. And we'll compare that to mass a little bit later. We're used to pounds in the English system, but the international system would call them newtons. And we oftentimes joke that you could walk into McDonald's and ask them for a Newton burger, which would, of course, be a quarter pounder, and let's see what the response is. But most of them just kind of stare at you. But a newton is roughly a quarter of a pound, and that's what we're going to use as our main unit of measurement. So, all the forces that we interact with really boil down to four main ones. Now, you're not going to have to memorize these. We're going to be talking about gravitational force a little bit later on, but some of these other forces are other fundamental forces that just sort of exist, and we're kind of learning why, but they're, as far as we know, they can't be broken down into any other components. There's something called the strong nuclear force, and that's really what holds an atom together. That is the nucleus of an atom together. The electromagnetic force, we use this every single day. That is the tendency of atoms to join together because of the pull of electromagnetism, really. Atoms join and chemical bonds take place because of electromagnetism. Weak nuclear force, this is it just has to do with the decay of radioactive particles. And of course, the gravitational force, we're all familiar with gravity. And interestingly enough, we think of gravity as being this big thing, this big force that holds us onto Earth, but really, with comparison to the electromagnetic force, like the same force that causes your hair to stand up and causes maybe a balloon to stick to the wall or to stick to a sweater on a dry day, compared to the electromagnetic force, the gravitational force is actually kind of weak. It's actually not very strong. The electromagnetic force is a quite strong force. But anyway, all these are forces that we interact with on a daily basis. So pretty much everything we see and can touch can really be boiled down to one of these four. That being said, look at what we call macro forces, or that is what you can observe just sort of on the day-to-day, on sort of a human scale. So this force right here, the net force, is not a fifth force. Net simply means how should we say this? Well, think of it this way. You make, let's say you go to work and you make $100. You gross, all right, $100 at your work, all right? Then, of course, a tax man comes along. So taxes are taken out. So taxes, I don't know, I'm going to make something up, minus $20, okay? So your net, what you bring home, your net pay is going to be $80. All right. So in this case, the net force isn't describing the force. It means After everything's been added up and subtracted, what is left? What is what really counts? All right, for you, what really counts is that 80 bucks. Yeah, the 100 bucks would be great, but you're not going to see all of it. So the net, what really counts, what really affects you is that $80. Okay, so of all the forces that we mentioned, the net force is not a fifth one. It's just sort of considering all the forces, what actually matters. All right, so we tally all the forces up when more than one force is acting. It creates the net force or the total force. And that's what I'm going to write in here, or the net, so the total force, or, yeah, net force, okay? So it's not a kind, it's just sort of, in the end, what is it, that determines how the motion will be affected, okay? So that's what this is right here, this Greek letter, and that is the Greek letter sigma, okay? And what it really means is the sum, S-U-M. Okay, so it's kind of like saying the sum of all the forces. Some are plus, some are negative. If you add them all up, what do you get in the end? Okay, that's the net force. So it's the vector sum of all the forces acting on an object in a given direction. So you add them all up, and what do you get? All right, the net force. So we're going to start looking at 3 different laws of motion that Newton proposed and seem to be holding up pretty well. This first law of motion, we're going to abbreviate N1L, Newton's first law, and that has to do with inertia. All right, an object at rest remains at rest as long as no net external force acts on it. That word net right there is going to be important. You probably heard it say like an object at rest will stay at rest unless acted upon by an outside force. Usually that outside force is that net force that causes it to actually move. But there could be lots of internal forces that add up to 0. All right, the net force is what really matters. So if the net force on an object is 0, then it's going to have a constant velocity. Now that's interesting. It doesn't mean that it's going to be at rest. It means that it's going to have a constant velocity. So that means if it's moving, it's going to stay moving. If it's at rest, it's going to stay at rest. That's really what Newton's first law is saying. The second law, which we'll get into in greater detail, is probably one of the more famous equations in physics history. That is F equals ma, or really we should say the net force on an object equals mass times acceleration. We've talked about acceleration in kinematics. We're going to introduce the idea of mass to that and equate that to force. All right, so the acceleration of an object is proportional to the net force and inversely proportional to its mass. Okay? And thirdly, Newton's third law, you might know this as the action-reaction law. That is, for every force that acts on an object, there is a reaction force acting on a different object or in an opposite direction, but with equal magnitude. Okay? Equal and opposite is the force that is the way you probably have heard it said before. Okay? So it could be said that the force of object A acting on object B is the same thing as the force of B acting on object A, but just in the opposite direction. Okay, so for every single force, there's an equal and opposite, you might say, reaction force. All right, so that's the 3 forces that are all summed up. We're going to spend a little bit more time in Newton's first law. What's that? I say forces? I'm sorry. Those are Newton's 3 laws, and we're going to spend some time on Newton's first law, and then that'll wrap it up for this video segment, and then we'll get into the second one later. Okay. The first law of motion, also known as the law of inertia. If something is inert, all right, like in chemistry, you may have heard of inert gases. They don't react with anything. All right, they just kind of do their own thing. They're not prone to change. All right. Well, inertia really comes from that word. Your tendency to keep moving at whatever velocity. Maybe moving is the wrong word. Your tendency to remain at the velocity that you're at, even if that velocity is 0. Okay, so it'll stay at rest if it's no net force that is acting on it, or it will maintain a constant velocity, moving in some direction as long as no net external force acts on it. But the big thing is the net external force. If there's no net external force, then your velocity is going to be constant. Okay? That's the same thing that causes you to if your car comes to a stop very quickly, it causes you to move forward. All right, because your car, which is kind of one great big mechanical object, all the parts are connected, it stops all at once, but you tend to want to keep moving, and so you have a tendency to resist stopping or resist changing your velocity, and so that inertia is going to carry you forward. So let's talk a little bit about inertial frames of reference. All right, a frame of reference is simply your perception about what is moving. All right, let's say right now you're probably sitting in a chair or you're watching this video. Are you at rest or are you not? All right, well, it depends on what your frame of reference is. Compared to somebody sitting across the room from you, you're at rest. You're both in the same frame of reference. Okay, you have the same velocity. You're moving with the constant velocity. For all you know, your velocity is 0, right? However, from a different frame of reference, especially the frame of reference of the rest of the universe, you definitely are moving. You're moving because you're rotating around the Earth is revolving around the sun, and etc. All right? So, if you're in what we call an inertial reference frame, inertial, all right, that means that you do not perceive any acceleration. All right? You don't perceive any change in velocity. You could be moving at a constant rate, or you could be at rest at a constant rate, but you're not perceiving any acceleration, any change in velocity. Your velocity is not changing, all right? You have inertia, you might say. Observers in different inertial reference frames will agree on objects' accelerations and the forces that cause them. All right, so if you look out at the universe, you can see the rest of the universe moving because the stars move around and the planets and so on and so forth. And the rest of the universe can look at you and see you moving. All right, and so whatever is causing that motion, observers in those different reference frames, inertial reference frames, will be able to perceive those differences in motion. But if you and another person are in, let's say I have the train example up here. All right, if you're in a train with no windows, you're sitting there, and let's say it's a really, really, really smooth train, and you don't know if you're moving. How are you able to tell if you're moving or not? And the answer is you aren't able to, because you and the other person are both in the same frame of reference. All right, only compared to if you were able to look out a window and see somebody outside in a field somewhere, you would be able to perceive, oh, okay, we're in different inertial reference frames because I'm moving away from that person. Who knows whether the train is stationary and the field is moving away, or the field is stationary and the train is moving away. But that's kind of the, at least the thought experiment to picture inertial reference frames. All right? So, if you have an inertial reference frame, you must have a non-inertial reference frame. Well, what does that mean? It simply means that that reference frame is accelerating. All right. Let's say you're in an elevator with no windows, as many elevators don't have windows. I know some of them are glass that you can see out, but so you're in an elevator. How can you tell that your elevator is moving? All right. Well, especially when the elevator starts moving up or down, you feel that jerk, that kind of the pit of your stomach drop out, and you can perceive some sort of acceleration. You're in an inertial reference frame. Now, interestingly enough, elevators, once they accelerate up to speed and start moving at a constant rate, then it's more difficult to tell that you're moving. But if there is an acceleration taking place, speeding up or slowing down, like when your elevator starts to get to the floor that you're going to, you can feel it's slowing down. You can perceive a change in your velocity, and so you can say that you're in a non-inertial reference frame. All right, but depending on how the frame is accelerating, that'll determine how the laws of physics act on that reference frame. All right. Sometimes we have to invent fictitious forces to explain why you're moving, and we'll talk about or why you feel a certain acceleration, and we'll talk about that in just a second. Well, I haven't mentioned down here at the bottom here, but we're going to mention fictitious forces on the next slide. This is a good example. Your car turning around a curve. All right, the car is moving around a curve. So here's your car right here, and it's going around a curve. I didn't really leave much space for myself, did I? It's turning to the left, okay? Like that right there. So you're here, you're sitting, let's see, we'll make you a blue dot. you're sitting in your car on the left-hand side, and what do you feel as the car turns to the left? You feel yourself pushed to the right-hand side, right? That's, sorry, I didn't really draw the car very well. The car is turning at an angle right here. Let's see. So there's a long, yeah. Okay, so this is the front of the car right there. So you feel yourself pushed to, this would be the right-hand side of the car right there. You say, hey, something's pushing me. No, nothing's pushing you. What happens is your reference frame is actually accelerating away from you. Why do you feel pushed to the outside? Well, because you have a tendency to not want to change your inertia. You tend to want to move in a straight line. So even though the car is curving to the left, you want to move in a straight line, and so you feel this perceived push to the outside or to the right side of the car. Right? That's not really happening, but it's a fictitious force. It's a fictitious force that many of us call centrifugal force. All right? Centrifugal force right here. When we get to talking about rotating objects, we're going to give that a different name. It's going to be centripetal force. But centrifugal force is hey, I'm being pushed to the outside of my car. No, you aren't. It's simply the fact that your car, your reference frame, is curving away from you. All right? And you're simply trying to move in a straight line because of inertia. So these fictitious forces, pseudo forces, do not actually exist. All right? Nothing is causing that, but it's a change in the reference frame itself. All right, you've got a non-inertial reference frame causing that. The Coriolis force. Now, I talk about this in earth science. It's not really a force, and so I don't call it the Coriolis force. We call it the Coriolis effect sometimes. An effect is kind of a perceived force or perceived going on. But that is the idea that a fluid moving over Earth's surface is going to curve one way or the other. All of that is because the Earth is turning. The Earth is a non-inertial reference frame. All right, and so that's why people say that if you flush your toilet in Australia, it's going to swirl a different way in North America. Well, probably not on that small of a scale, but when you talk about great big ocean currents and the direction that they curve, yeah, you're right. All right, but it's not because of an actual force. It's simply because the Earth is a non-inertial reference frame and it's turning. All right, so we need to establish the fact that there are some fictitious forces and describe actually why they exist or why they appear to exist. They exist because of other actual forces. So, just got done talking about inertial and non-inertial reference frames. So Earth's surface, where we live, where we do all of our experiments, is that inertial or is it non-inertial? Because after all, we know that the Earth is rotating on its axis, right? It's spinning around. It's revolving around the sun. The sun is orbiting the center of the Milky Way. The Milky Way is shooting away from all the other galaxies in the universe. And so we definitely are living in a non-inertial reference frame, okay? The surface of the Earth is definitely non-inertial. But all these accelerations and the motion of the Earth with regards to the sun and the rest of the universe are so small, and at least on a human level, imperceptible, that we could say, for practical purposes, that the surface of the Earth is very much an approximation of an inertial frame of reference. Like I said, if you're in a room with one other person, and let's say the room has no windows, okay, you can't perceive any of the outside universe, just between you and that person, are you moving? You probably can't tell that you're moving, all right? So if any kind of experiment that you do, it will appear to be in an inertial frame of reference. That is, that you are not accelerating. And that's the key. You can be moving, just not accelerating. All right. When we talk about motion over Earth's surface, we talk about great distances, we have to start taking into account the fact that the Earth is in a non-inertial reference frame. But for small distances in a laboratory or in your classroom or at home, we're going to assume that we are living in an inertial reference frame and that there's no perceptible acceleration going on due to motion. All right. Well, that's going to be it for this section right here. It took quite a while. We're coming up on 20 minutes, and I thank you for hanging in there. But we've laid the groundwork for a lot of a lot of discussions that we're going to talk about a little bit later. So thanks for following along. In the meantime, if you have any questions, make sure you see me, and I'll see you on the next one. Take care.